This video is sponsored by PCBWay.
When PCBWay approached me to do a project together, I knew exactly what I wanted to try. I think it's crazy that we quite possibly could have stumbled across a world first here, but if you know of a project that predates this one, let us know in the comments. In this video, I'm going to try to answer any questions you might have and let you know how you can get your own glow-in-the-dark circuit boards. Okay, bear with me while I paint a picture for you. It's the late 80s, early 90s, and bright colors are all the rage. As you can see here, our fashion was made up of lots of bright fluorescence. And here I am on the left, my brother and sister on the right, and check out what they're wearing, fluorescent green. I also love fluorescent green because I ended up getting this hat from, looks like my uncle, for my birthday, and I wore that hat quite a bit. I don't remember what happened to it, but it was one of my favorites. Don't tell my skateboarding friends, but I also had a pair of black and fluorescent orange rollerblades growing up. And fluorescence didn't come just in fashion, but in toys as well. And though I don't look so enthused in this picture, that construct set actually ended up being one of my favorites. Due to my love for fluorescent green, it naturally attracted me to glow-in-the-dark items. And as you can see here, I kept my construct set, although I guess mixed with my robotic set, from 30 years ago. And there's the glowing elements that it had in it. I also kept several toys that I had from over the years, and even some glow-in-the-dark tattoos, Transformers and Ninja Turtles over here. Let me brighten that up. I also kept a sticker book from back in the day, and I'll never guess what it has in it. Jurassic Park stickers, classic. But on this next page you'll see these, and on these next pages here, these two. These are the cutouts from them, but these stars are what almost every 80s kid had on their ceiling because they were glow-in-the-dark. I was wondering if these glow-in-the-dark stars are still sold today. Turns out they are.
Okay, let's get into the meat of this video. So I came up with a list of questions that I thought you guys might be curious about. If you're listening to this video rather than watching, some of the questions are, what is glow, and what's the best way to measure it? What's the best wavelength, the best strength in watts of the light source? What's the fastest charge time, and what gives us the longest glow time? And lastly, how does the PCBWay circuit board compare to other glowing materials? While I'm not a science channel, as a technologist I live in the tension between the practical and the theoretical. So we're going to dip into some theory so everything can make sense. So glow is photoluminescence, and there are two areas of photoluminescence. One is fluorescence, and the other one is phosphorescence. So fluorescence is when a photon is absorbed and then raised to an excited state and then emitted at a different wavelength, but it's a temporary process. And phosphorescence is essentially the same thing, except that it actually re-emits the photon for a longer period of time. So in the case of phosphorescence, invisible UV light is then re-emitted as visible greenish light. And since blue light is shorter on the spectrum than green, it can also help phosphorescent materials to glow. And speaking of wavelength, here's an electromagnetic spectrum diagram that shows the wavelengths of both invisible and visible light. In the experiments to follow, we'll be focusing on the 200 to 500 nanometer range. So we'll be messing around with blue light all the way down to UVC light. I know I'm not the best at explaining theory, so I'm going to put some links in the description for you. Some to some YouTube videos that are helpful, and some to some Wikipedia articles. Okay, let's move on to the testing phase. The things we'll need will be a dark environment, a camera to see what's going on, a light sensor of some sort, some electronics to read the light sensor, and software to interface with electronics and give us a readout of our data. While we have yet to choose the sensor, I do have the rest of the items figured out. So we have an ammo can with camera inside, an EasyBV4 by Easy Robot for the electronics, and the ARC software by Synthium for real-time data analysis and data logging.
And here are the sensors. If it looks like they're mostly solar panels, that's because they are. So solar panels are called photovoltaic, and they can convert light into voltage. Solar panels, or solar cells as they're often called, come in two varieties.
polycrystalline and monocrystalline. Monocrystalline cells are commonly found on little solar-powered calculators. They're quite sensitive to light, but don't output very much current. And polycrystalline are a little bit of the opposite. They aren't very sensitive, but when they do pick up light, they can produce quite a bit of current. On this list, I also have a small array of photodiodes and a couple of CDS cells, which are also called light-dependent resistors. Here's a simple wiring diagram which shows how to connect each type of sensor to the EasyBV4. One thing you may have noticed is that I wasn't using a lux meter as a sensor. Well, that's because I actually don't have any. Well, besides the lux meter apps that you can get for your smartphone, but I don't find those to be very reliable. I figured that since I'm a robot guy, I've got a ton of sensors kicking around, so maybe I just DIY one instead. So my goal was to find a sensor that was pretty sensitive to phosphorescence, but still had a smooth response. So in order to compare these sensors to each other, I needed to find something that phosphoresced really well. In my collection of glow-in-the-dark items, I found this nice and bright glowing tent peg. I teamed that up with a 365 nanometer UV flashlight, and I was off to the races. So pay close attention to the graph on the left, and you can see how sensitive each of the sensors is. Some of them were not very sensitive at all, but there was a few, like the monocrystalline solar cells, that were decently sensitive, and the photodiodes were fairly sensitive, but in the end, the CDS cells ended up winning. I actually came across this weird response that some of the monocrystalline cells exhibited. Same with the photodiodes. The signal would kind of bounce up and down, as you can see here, and it was just kind of a bit erratic, not a very smooth response at all. So I think it was something to do with the current output. They just can't put out much amps at all. And here you can see the larger of the two CDS cells has a nice smooth response and is quite sensitive from the beginning. So we'll proceed with using the larger CDS cell to do all the measurements from here on in.
Okay, my wife's gone, so we only have so much time to do this. Let's get it done. We got probably close to 500 of these star stickers here, so we'll see how many we can get put up before she gets home. Got it close to the light. This doesn't work really well on a popcorn ceiling, I guess.
So I know this is a bit of a disruption to the video, but I wanted to give you guys a small break before we get back into some analysis.
Yeah, I can kind of see it. I think she'll be surprised. Maybe a little angry. Oh, we made it just in time. She just arrived.
Later that night.
So did you notice anything different about our room?
Well, I did see the glow-in-the-dark stars, but I thought maybe I just hadn't noticed them for a while because they weren't charging properly, but I don't remember seeing them.
Yep, these are new.
The phosphor lighting up in these bulbs is pretty neat.
You almost blinded me with that thing.
Sorry.
Okay, let's get back to it. Now that we have our sensor figured out, let's move on to testing it against the PCBWay glow-in-the-dark PCB. So if you look closely, on top of the purple layer, which is called the solder mask, is the white layer, which is called the silkscreen. You'll notice on top of the silkscreen there's kind of a translucent layer, and that's the glow-in-the-dark material. So what we want to do is find the most concentrated spot of this glow-in-the-dark material so we can test it with our sensor. So the most concentrated spots are probably around the logos or around these larger electrolytic caps. I think this is going to be our spot. The C1 label is closer to the middle, so I think that's going to be where we test. So here are the light sources that we'll be testing. We have a few sanitizers, we have a few flashlights, and some LEDs. So I needed a way to keep the sensor stable, but still have the ability to slide the PCB in and out easily. So I ended up using one of my 3D printed comic book stands that I designed a while back. Alright, here's the test setup for testing out the different light sources. This isn't a test, but I wanted to show you how cool the PCB looks when fully charged. Ooh, So here's the process. So we take our light source and we illuminate the C1 footprint for a certain duration of time.
We then slide the PCB under the sensor, close the lid to the enclosure to make sure it's super dark, and then we start our data logging process in the ARC software. One thing I failed to mention is that we're not actually getting empirical light measurements here, but rather just the amount of glow time, because that's the most important. One really nice feature in ARC is that it actually tells you how long you've run your script for, so I didn't actually have to go into the CSV file to find out how long the glow time was. From here on in, it's lather, rinse, repeat for all the different light sources at different charge time intervals. For each light source, I did multiple charge time intervals with 3 samples per interval. I do have to admit that I didn't put that much time into testing the UV sanitizers. As I found out quickly, the UVC light just doesn't charge up the phosphorescent coating very well. And here are the results. So the UVC light actually has the slowest charging rate of all the different types of light, and it doesn't give us much glow time. The 365 nanometer UVA light actually did pretty decent. It gave us a quick charge time and gave us a long glow time. But the best results actually came from our 395 nanometer UVA light, which gave us a fast charge time with the longest glow rate. One thing I was super curious about was the results from the blue light. When compared to UVA, it has a much slower charge time, but the crazy part is that it has about the same amount of glow time. Alright, here's a summary of the answers to our questions. For number 1, what is glow? That's phosphorescence. Number 2, what is the best sensor to measure glow? That's the 11mm CDS cell. What is the best wavelength of light to make the PCB glow? That's 395 nanometers. What's the best strength in watts to use? The stronger the light, the better. What wavelength gives us the fastest charge time? That's again 395 nanometers. What is the maximum glow time for the PCB? It's about 3 minutes. And how does the PCB compare to other glowing materials? Well, it doesn't last as long because there's a much smaller amount than compared to the other materials. So my curiosity got the best of me, and I did a little side quest out on the open road. Have you ever seen those streetlights where the phosphor coating is actually peeling off, revealing the blue LED underneath? I wanted to see how well that blue light caused the phosphorescence effect. Alright, you can see that there's lots of glow, lots of traffic. Alright, let's put this to the test. You can see here I did a pretty good job at fluorescing these plastic bits and this uranium glass. But when I tested it with phosphorescent glow-in-the-dark material, the results weren't that great. You can see here I charged it up for a little while, then brought it into the darkness, and the glow was just not that bright. So when I tested the less sensitive printed circuit board, as you might have guessed it, the results were even poorer. I couldn't see any detectable glow. Well, it was worth a shot. Alright, let's move on to our final tests. Here we're going to test the PCBWay circuit board compared to other materials. In these tests, we're going to use our best UVA light source teamed up with our sensor taped directly to the material. And for each material, we're only going to use 1 second of charge time. So for once, I'm just going to keep quiet and let's do a little montage. So here are the results, and some of it's quite surprising. Off a 1 second charge, some of these paints glowed for almost 2 hours. I mean, if the paint was in a thinner layer, like we have on the PCB, we'd likely see that number go way down. I was also pleasantly surprised by the glow-in-the-dark resin that I purchased. It actually glowed quite a long time as well. But maybe that's because it had the rock's power behind it. Sorry, but I needed to do just one last side quest. I had to. I was wondering what would happen if I took the glow-in-the-dark resin and put it on top of another PCB to kind of emulate what PCBWay did. I was thinking, why not try my own glow-in-the-dark PCB prototypes at home? I was pleasantly surprised that it actually did kind of work, but not near as effective as PCBWay's circuit boards. Okay, before we close this video out, let's talk about some potential applications of this kind of technology. I love some of these ideas, like
using the glow-in-the-dark coating to embed hidden Easter eggs for escape room props or gadget geocaches, or using it to mark out important test points or traces for easier troubleshooting and debugging. I think it'd be awesome to use it as a new effect for con badges as well. If you don't see one of your ideas here, definitely throw it down in the comments. Don't worry, I didn't forget. If you want to get your own glow-in-the-dark PCBs made, you're going to have to go to the Contact Us page on PCBWay's website, because they just don't have it as an option yet until there's a lot more interest. Oh, and one last thing, PCBWay actually has multiple colors of glow-in-the-dark available.
I know we jumped into things rather quickly, so let's end on an introduction. My name is Jeremy, and I go by Bot Matrix on all the socials. This is a bit of a channel revive for me, since I've now decided to get into content creation part-time. But in order to make this a reality, I'm going to need your help. If you'd like to support this type of content, sign up for a Patreon tier that fits you best. And finally, thanks for watching.